Okay, let's get started. So last class, we did equivalent circuit model of our induction machine, which is a rotating transformer. So if you recall, our equivalent circuit now has the value of S, which is a way of introducing in frequency. But we also wanted to reflect impedances, resistors, inductors, to the quote unquote high side or the stationary side of the AC machine. So we're going to look at an example here. We're going to be able to calculate all the important parameters and actually have a pretty good circuit representation, and we can calculate a lot of different things. So I'm going to show you two ways. The way we'll do it in the notes is just to basically use some Thevenin equivalencies and series parallels. And then the other way I'm going to show you is to actually write loop equations. If you write loop equations, you actually have a little more information, because not only do you have the stator current, but you also have the rotor current. So it really gives you a lot of information, and then you can very quickly calculate any parameter that you want, losses and all that stuff. So we have a 460 volt, 25 horsepower, 60 hertz, 4-pole, Y-connected induction motor. Again, we got to look at what the relevant stuff for us is. So we see that we have some speed. Speed immediately tells me I need to know two things. I need to know frequency, and I need to know the number of poles, because once we have that, then we can estimate what the synchronous speed is, or actually calculate what the synchronous speed is. And we can't calculate the actual mechanical speed of operation unless we know what the sync speed is. We also know that it's 460 volt and Y connected. That's important for us because we've got to calculate the stator current. So knowing 460 and that it's Y connected is relatively important. It's an induction motor, so we want to go ahead and develop or come up with an equivalent circuit. Again, we're looking at circuit analysis, so that induction motor part tells us what the equivalent circuit model is. The 25 horsepower is not relevant to us for doing calculations. That, again, is the nameplate rating of the machine. That is not relevant to us because it doesn't really necessarily mean that that machine is operated at 25 horsepower. It operates at whatever is necessary as demanded by the load at a specific speed. We definitely want to go ahead and include these parameters. These are pretty important to us. So we have our resistors and inductors. Yes, sir.
Environment we use the 25 horsepower.
Oh, so what the question is, what environment would use 25 horsepower? That's just when you specify. So if you have a load, you would specify a 25 horsepower rated machine. So it's just the capability of the machine. It's not necessarily what it's producing. It's what the capability of the machine is. So you would need to know what the mechanical load requires, and then you would specify it up to 20. This thing can put up to 25 horsepower. So as long as you have a machine that can exceed the rating of it and operates at the same speed, then you would use this as a specification only.
What do you define the torque? If you ask for the torque, you did ask for the.
That's true, but our mechanical engineering friends would tell us that there's a torque, a speed versus torque. And depending on what speed you're operating at, the torque kind of changes. So if you think about a pump, there's a torque versus speed characteristic that actually, as you increase the speed, you need more torque because you're pumping more water until you get to right about here. And then what happens when you're pumping a lot of liquids and stuff like that, you get cavitation. Anybody know what cavitation is?
It's like instant vaporization or boiling in water.
Yeah, the air and the stuff that's trapped in the water, it actually gets released. And it ends up happening is now you have air that is in your fluid. So you no longer have a homogeneous substance, you have air bubbles, and that has a different density than the water. And so when you pump has water and then air and then water there, it vibrates. And the cavitation is a vibration as a result of running it at too high of speed. So if you get above this point, you start to get cavitation, and then torque goes down because then it's hitting water, then it's hitting air, and actually the pump won't last very long. So the reason why you can't use torque is because you need to know what speed of operation it's going to be. So that again is going to have to come from the mechanical engineers. The mechanical engineers are going to say that this torque versus speed curve is at about here, and I need you to give me 22.3 horsepower at 1650 RPM. And then you would specify the motor application. Actually, most of the time, the mechanical engineers, what do? They just say, well, I need a skid. I need a pump and a motor all coupled together. Anybody guess as to why they do that? Why would you buy it as an assembly, essentially? Well, you hope it works, but there's a huge reason. Remember, we live in a mechanical world. Electrically, our lives are really easy. We can walk up to an electrical load and we can wire it up. Wires go every which way. Doesn't have to look pretty, but it works. How about our friends in mechanical engineering? They need torque. They need to move something. So if your pump is here and your motor is here, they better be aligned pretty perfectly. Because what happens if the motor is this way? Now, even off by a degree, you actually can get the torque, and you can actually get tension. You can get things breaking. They don't always work. And so one of the things that mechanical engineers have to deal with is a term called a shim. You know what a shim is? Just a little thin piece of metal. You slide underneath the feet of stuff and you help line it up. And usually you have to be lined up like within a millimeter or a thousandth of an inch. Really accurate. And so a lot of times mechanical engineers say, that's a lot of work to line things up because you got to pour a concrete slab. And then normally you put iron rails in it to go ahead because the concrete will move over time. The iron is usually pretty set, but the iron usually is a very flat surface. Okay, so you can use that as a support. But then the other thing too is when you bolt things down, sometimes you take up too much material. Sometimes you screw things in too tight. It can be a problem. So what do? You just order a skid from a manufacturer and then you say, give me the skid, and it's all lined up already. There's a motor location here, the pump location here. They're all coupled together. And actually they can ship them separately, but usually you just set it on here and it's a pretty easy process to do that. So most mechanical systems, unless you have a really complicated system, it's far, far, far better to go ahead and just buy it on a skid. So like, why would we buy an air compressor? An air compressor has a motor with a compressor. You go to Home Depot and it all is one assembly because everything lines up perfectly. So buy a skid, or have the mechanical engineers buy a skid typically. You just have to worry about the electrical. So we need that. We need some rotational losses. Core losses is negligible or included in rotational. And the last thing we need is slip. Okay. Those are all the important stuff. We need a lot of information to be able to make this work. So the first thing we'll calculate is the speed. So we need to know for a 4-pole machine, what is the synchronous speed? 1800 RPM. Hopefully you're starting to memorize that just by looking at it all the time. And since we have a slip of 2%, or 2.2%, I should say, we can use our equation to calculate mechanical speed from synchronous speed and the slip. So this machine runs at 1760 RPM. This is actually the current application. Somebody measured that it's running at 2.2. Now we've got to go ahead and calculate our parameters. So we have to actually build our circuit over here. And we've got to go ahead and start calculating what the Z in is of this entire application, the equivalent circuit. So this would be Z in or Z Thevenin. Now, however you want to do that, that's whatever you want. But you can see that I have these two in series, which are in parallel with these two. Keep in mind, you didn't get any core losses, so we'll just assume that that's infinity. So you have those two in series, which are in parallel with Jx of m, and then you just have a series circuit so you can calculate it. The only other thing we need is V phase. What is V phase on this particular application? The problem description said 460, right? But it's Y connected. So this application here is a single phase representation of the motor. We need 3 of them to fully represent the motor. And so the phase voltage is going to be 460 divided by the square root of 3. In AC circuits, we have magnitude and angle, and we're just going to pick that as our reference. Okay? So the applied voltage is 460 divided by square root of 3 at an angle of 0. And now we have to go ahead and calculate our impedances. So the first thing we do is we add those two in series, R2 over S plus JX2. We get a certain value. Now we got to go and do the parallel combination of JXM and our Z2. We end up with 12.94. Continuing, our total is the stator, the Z1 and the Z1, which is R1 and JX1, plus the parallel combination that we have. We end up with 14.07. Now our current going into the machine is just V divided by I. It is Ohm's law at this point. So my current going in is 18.9 at an angle of minus 33.6 degrees. That's the current that this particular motor sees. Why do we calculate the angle? Because most of us as electrical engineers are only really interested in what cable size do I need. So I've got to run a 460 volt, 25 horsepower motor that's going to be operated at slip. Then it's going to be pulling around 19 amps. So I can probably get by with a number 12 conductor to go ahead and feed that, because a number 12 conductor is good for 20 amps. Number 12 conductor is only interested in the magnitude of the wire, but I also want to know about the power factor. So I need the angle between the voltage and the current to be able to calculate the power factor. So that's the reason why I include it. I have 0.833. Note that it's not negative 0.833, it's a lagging power factor. Why? Because the current lags the voltage. Okay? And that's when I'll calculate my power factor. By the way, this is a pretty low power factor, right? So the utility is going to charge us some money because our power factor is so low. But this is a pretty typical, pretty realistic power factor for a lot of induction motors. Now our input power, we're going to use line quantities. And remember, the phase current and the line current is the same in a Y, but the phase voltage and the line voltage are different by the square root of 3. So if I'm using the square root of 3 multiplier here, I've got to make sure that I'm using the line voltage, which in this case is 460 volt. So square root of 3, VLIL cosine theta is equal to 12,530 watts. Stator copper losses, now it's just I squared R losses. And I've got 3 stator windings. So that means I have to have 3 times the individual one, which means I'm consuming 685 watts. My air gap power, this is the power that goes from the stationary world to the rotary world, right? So that's the one that jumps across the air gap. And that power is determined by subtracting your stator copper losses from your input power. So we're at 1100 or 11,845 watts. My converted power, this is now the power that actually gets converted to mechanical power, okay? So it is 1 minus S times the air gap. The other option you can do is you can see that it's P air gap minus P rotor copper losses. Either one of those will give you the same results. You can just subtract the two, but this is the one we developed last class. We have the 1 minus S times the air gap. And then our output power is our converted power minus any friction and windage losses, because friction and windage losses are all mechanical. So we're at 10.5 kW. We convert that to horsepower, and remember at the beginning of the problem, 25 horsepower motor, is it really running at 25 horsepower? Absolutely not. It's running at 14 horsepower, which the motor is perfectly fine to do. You can run the motor, as long as you don't run it over nameplate, the motor doesn't care. It's perfectly happy to do that. In fact, as you get more and more horsepower, the motor becomes more efficient, right? It operates at a higher or a lower slip, which means higher efficiency. But this motor has way more capacity than what's necessary. So it'll last for a long time. As long as you keep the bearings in good shape and you keep it clean, you're running at almost half its rating, so won't have any issues with it. Now I'm going to go ahead and calculate my induced torque. Air gap power divided by synchronous speed, 62.8. These are in Newton meters. My load torque, this is the actual torque that is available mechanically, is the output power divided by the actual speed of operation, 56.9 Newton meters. And then lastly, my efficiency, P out over P in, is 83.7%, which is pretty low. Yes, sir.
The induced torque, is it the torque if the one?
Nope. So the induced torque is the actual torque that is available mechanically. Not available to the load, it's available mechanically. What's gonna gobble some of that up? Friction and windage losses. The friction and windage is gonna go ahead and take some of that power away. So we need to provide a torque, right, that is able to overcome the losses because of friction and windage. That's what that is. The load torque is actually what's available to drive a load. Make sense?
I'm trying to see, you have the schematic that shows.
That shows the power going away, yeah.
Yeah, but then which, I'm to see at which point do we have the.
We can do it ourselves, right? So this is P in. Then we drop off stator copper losses. If we have them separate, we drop off core losses. And at this point, all the power jumps across the air gap. Okay, still mechanical, still electrical, but it's jumping across the air gap. Now I drop off any rotor copper losses, and at this point, this is converted power, which I can get from my induced power, because everything at this point now has been converted from electrical to mechanical. So now I'm in a mechanical land, so I drop off any friction and windage. And then this is P out, which is my load torque times mechanical speed. So you're just dropping off power as you go through the circuit.
But then why didn't you use the power column instead of using to find the induced or induce the power in the air gap instead of using.
Why did I use P air gap? All right, you want to use P converted? That's fine. So P induced is equal to P converted divided by omega sub m, right?
Mm-hmm.
But isn't P converted 1 minus S times the air gap? And isn't omega sub m 1 minus S times omega S? So you could have used it. Doesn't matter. It's the same thing, right? It's just that we just didn't have to, well, we didn't actually calculate omega sub S. I mean, omega sub S in radians per second. We calculated in RPM. So it doesn't really matter. But yeah, that would have worked perfectly fine. Okay. Here's another way to do it. And I'm going to clear this out. Give me some room. Okay. So what's a better way to do it, in my opinion, is what is a really good circuit analysis technique to analyze this circuit without having to do all these combinations and things. Remember, we'll delete this one. Actually, let's redraw it without that one. So R1, JX1, JXM, JX2. And I'm going to break these two up. This is R2. This is R2 times 1 minus S over S. And this voltage here, oops, didn't go quite far enough. This is V phase at an angle of 0. So do you have another way to analyze a circuit without doing the series parallel combinations? Your friend and mine. How about doing loop equations? Remember loop equations from circuits days? And the reason why loop equations are really good is because I have I1. And if I choose this correctly, I2, this is going to give me the stator copper losses. This is also going to give me rotor copper losses. And this is going to be able to give me directly my converted power. Because it's I squared times R. Remember, the R2 times 1 minus S over S is the actual equivalent resistor to what the mechanical power conversion is. So by knowing I1 and I2, instead of combining it, I can get way more information. So I'm going to go ahead and do these generically. So if I'm going too fast, let me know. Minus to plus, plus to minus, 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 and plus to minus. Everybody agree with that? Just doing the loops in the direction of the current. So what I think most electrical engineering students or EET students, what we like to do is we say it's the sum of the voltage drops is going to be equal to 0. So a voltage drop that is actually a rise is a negative voltage drop, right? So we have negative V phase plus I1 times RI1 plus JX1 plus JXM. That's all the voltage drops because of I1. But don't forget, I have a negative voltage drop because of XM. So that's minus I2 times JXM. That's going to equal 0. That's my first loop equation. My second loop equation, because of symmetry, minus I1 JXM plus I2 times R2 R plus R2 times 1 minus S over S plus J times XM plus X2, and that's going to be equal to 0. Okay. Now, I said this is actually better with information, but oh boy, it doesn't look better to me. What might be better is to figure out a way to directly solve for them. So let's do some linear algebra. So we're going to move the knowns to one side of the equation and then move the unknowns to the other side of the equation. So I have V0 and 0 in a matrix is going to be equal to R1 plus J, X1 plus XM, minus JXM. And that multiplies my I1 and my I2 variables, which are unknown. And then it's a symmetrical matrix, minus JXM. And this one becomes, let's see, we'll just call this R2 over S plus J times XM plus X2. Remember that from linear algebra when you first taught algebra? Don't remember this? Yes, sir. I combined these two because I just didn't want this equation to get forever. But yeah, you can combine them and get that, or you can just keep them separately. It's the same, if they're equivalent to each other. Anybody not sure how to get there from here? Speak up now. It's a perfect time to do it. Because if you can use matrices, it really makes your life a lot easier. Because now I have a V matrix, which is equal to an impedance matrix times a current matrix. My V matrix is in volts. My impedance matrix is in ohms. And my current matrix is in amps. But I already know what these are. I know what the voltages are. These are the knowns. This is the unknown. So I want to solve for I1 and I2, which means I have to do a little bit of algebra. But when I'm working with matrices, I've got to be careful because I have to make sure the dimensions of the matrix works. So this is a 2-row, right? By 1-column matrix. This is a 2-row by 2-column matrix. And this is a 2-row by 1-column matrix. So if I want to be able to solve properly, I need to make sure all the dimensions work out okay. And I want to solve for this matrix over here, which means I've got to get rid of this matrix. So if I multiply this by the inverse of this matrix, so this is Z, and if I multiply it by a Z inverse, this is a 2 by 2, this is a 2 by 2, that gets rid of this matrix, correct? But the problem is I multiplied this by a 2 by 2. And the thing about matrices is the inner dimensions have to match, and then the corresponding output dimensions is what the results are. So you can see the inner dimensions over here, the 1 and the 2 aren't the same. So I can't multiply both sides by Z inverse in the middle over here. That doesn't work. So what do? Change it up a little bit. And how about, let me move this over a little bit so I have some room. How about instead of post multiplying after the Z, what if I pre-multiplied? Oh, let's see, there's a 2. By Z inverse. I'm good over here still. I was okay over here. Now let's check on the other side. So I'm pre-multiplying. Do these two match? 2 and a 2 are the same. And the resulting matrix of multiplying those two will give me a 2 by 1. So the inner dimensions have to match, and then the corresponding output matrix has to be equal to the outer two ones. So does a 2 by 1 equal a 2 by 1? Looks good. So when you multiply matrices together, you got to be careful about pre and post multiplying your matrices. That's why when you multiply matrices in your calculator, sometimes you get the dimension error. You ever seen that or have that happen to you in your calculator? All of us had. That's because we just don't multiply in the correct order. Now, by the way, when I said when we multiply, the inner dimensions have to match and you get the outer dimensions. So wait a minute, Paul. You said that Z inverse times V equals I, but what about this matrix over here? It should be a 2 by 2 matrix, right? Where did it go? Should still be there, shouldn't it? If I multiply a 2 by 2 by a 2 by 2, that doesn't just make it go away. I still have that matrix there. It should be a 2 by 2 matrix over here. So why didn't I write that 2 by 2 matrix there? Nope, it's not all ones. Close. This is called the identity matrix. And it's not all ones. It only has ones on the diagonal. So when you multiply a matrix by the identity matrix, you get that exact same matrix. So you technically, if you want to be super mathematically rigorous, you should include the identity matrix in here. But most of us just say, you know what, it's the identity matrix. We don't have to include it because it's equal to I. So doing matrix multiplication is very helpful. You just have to be aware or be careful about when you pre and post multiply. Okay, does everybody remember the identity matrix from, I think that's pre-calculus, right? If you did pre-calculus? No?
No, we talked about it.
Well, that's because it's a linear algebra, but you use that all the time, they just represent it really quickly, but you should have been taught linear algebra in pre-calculus, usually. If you took MAT 122 here, I don't know if you all did, but if you took MAT 122, that's supposed to be a topic. And basic linear algebra is a pretty important feature for us to be able to do, especially in power systems, because it makes things easy. So now all I need to do to get my I1 and I2 is I multiply and I pre-multiply. So this is R1 plus J X1 plus XM. This is minus JXM minus JXM R2 over S plus J times XM plus X2, that whole quantity. And then I multiply that by V1 and 0. Oh, I forgot to say, this is the inverse of that matrix. And again, once I have that, I not only have the current going into the stator, but the equivalent rotor current. So I can calculate all those parameters. So I love me some MATLAB. I know you all don't, but let's do it anyway, because this is just doing it in your calculator. I'm not doing anything other than entering it in your calculator. So I put sync motor, it should be induction motor. Okay, so remember, clear and CLC just keeps me honest. Here are all my initial parameters, and I know, or I determined the number of poles because I knew that it was designed to run at 1800 RPM or around 1800 RPM. So you could calculate the number of poles from that. Then I went ahead and started calculating. So I calculated my synchronous speed, and I also calculated my synchronous speed, not only in radians per second, but in RPM. Then I calculated omega sub m, which is the mechanical speed in radians per second. I also did that conversion to RPM. Then I calculated this Z matrix over here. What is this Z matrix? That's the one that we just derived using using mesh equations. Now I'm going to solve for my I by inverting my Z. That's all that is. Zeta minus 1 is the same thing as inverting it. And you can see I'm pre-multiplying it by my V, my voltage matrix. And then I'm going to pull out I1 and I2 and display. Okay. So I'm going to go ahead and start simulating from here. So I'm going to set my breakpoint. Start running. And where is the actual, here we go. Try to make it smaller. Okay, so now we're going to go ahead and start running it. I guess I made it a little too small, so let's move over this way. Because I can't see the stepping part. All right, so I'm going to step. Now it's going to calculate omega S, but it's not going to display anything because I'm suppressing it. I don't really care about the synchronous stuff. I care about the mechanical actual operation. So here's what I get for the mechanical speed of operation in radians per second. And here's what I get in revolutions per minute. 1,760.4 RPM. Now I'm going to calculate Z. And again, I'm not going to display that because nobody's going to really care what that looks like. I'm going to calculate I. Then I'm going to pull out my stator current. And I'm going to display it. And I said our calculation was 18.88 at an angle of minus 33. MATLAB just has a little bit more precision. You know, it's keeping it all in there. So you can see that I get the value. This is exactly the stator current we calculated by doing the other approach. I'm going to continue and calculate my rotor. But why am I not displaying what the rotor current is? I don't need it. I'm not asking it for any of the problems, right? I don't need any of the specific details. So I'm just going to skip past that. So now I'm going to calculate my input power, and I'm just going to go 3 times V phase and the conjugate of I. And this is I going into the current. So whereas before I had to go square root of 3 VI cosine theta, I'm doing the same thing over here, but I'm actually solving for S as a complex number. And then I just pull out the real part of my input power. So my input power is 1,200 or 12,525 watts. Now I'm going to, well, I don't actually need to print it, but that's okay. We'll just do that again. My power factor is the cosine of the angle 0.8321. And this is where you're going to have to look at the angle. That's why I put that here. As you can see that the angle of the voltage is 0, the angle of this current is negative. So I put the power factor here and then recognize that the angle is negative. So you're going to have to be aware enough to go, this is a lagging power factor because of the negative angle between the voltage and the current. Now I'm going to go ahead and do converted power. So I'm going to do the converted power, which is I'm going to subtract the power from the stator and the rotor. So this is just doing the brute force method. Now that I have that rotor, I can actually go ahead and do this. And you notice it's just multiplied by R2, not R2 over S or anything like that. I'm just trying to get the rotor copper losses, which is R2. So I'm going to step, and I get 11,578. Let's compare that to the slide, which had 11,585 versus, what did I say it was? 11,578. So 585 versus 578. So that's just the precision of the calculations. It's only off, it's less than 1%. So that's just doing a different approach. Whereas over here, I said it was using P air gap minus times 1 minus S. This one, I just broke them up separately, and I'm getting essentially the same result. So you can certainly get there from here. Continuing on, now I'm going to get my air gap power. And notice I'm just taking away whatever the input power is, and I'm subtracting out the stator copper losses. So when I do that, I get 11,845, which let's see how that compares here. Whoops. So 11,839, again, off by about 6 watts. Let me undo this because I hit a button by mistake. All right, keep going. My output power is 10,478. Again, off by 7, not too far away. Continuing, now I'm going to have my induced torque and my load torque. So let's bring those up. And I've got 62.8 and 56.8, which I think are almost exactly that. Now I'm going to calculate efficiency. And my efficiency is 83.7%, which basically the same. So you can do either approach. It's up to you, whatever you feel more comfortable. I like the one that I suggested because all it does is you just look at the circuit. You don't have to remember what the air gap power is. You just look at the circuit and then you have this diagram and then you should be able to calculate all those parameters. Just recognizing in your equivalent circuit that R1 is the stator copper loss. So if you had to take a test, go ahead and put these are stator copper losses. This is R2 and then R2 times 1 minus S over S. This is rotor copper losses. And then this is the converted power. So if you just know that when you're doing your equivalent circuit, you can pretty quickly, without having to keep track of all those different things. Yes, sir.
So actually the delta copper losses the R1 and X1, right?
Say that again.
The stator copper losses.
Stator copper losses are just R1. It's not X1 because why does X1 have the losses?
And then the RC, what is the RC?
Core losses. And if you had to calculate the core losses, you'd have to somehow get this value of R sub C, which is very difficult to get. Most of the time, you just ignore it because it's pretty high anyway.
And then what is the R2 1 minus S over S?
So that's the combination of these two. So you have in your actual rotor circuit, you have R2, and then you have an output equivalent power, the actual power that gets converted to mechanical power. That is R2 times 1 minus S over S. When you add these two together, You can check it, but you should end up with. So that circuit that you see in front of you is the simplified version.
And then the outflow bias the water copper losses or just
No, R2 is the rotor copper losses. That's that one right there. The rotor copper losses are not dependent on the slip. It's just dependent on the current. The power output is dependent on the slip, the resistance. But keep in mind, in fact, the rotor copper losses are dependent on the slip because the higher this value is, the less current through there. So the less current means the less rotor copper loss. But the value of R2 itself doesn't change. Okay?
really easy when you do
It is, yeah. It's just a
it. When
circuit.
you do it's very easy.
When I do it or when you do it?
When you do
You'll get to do it too. How's that?
it.
So-
Do it, but not very easy.
Well, it's practice. I've done this a lot. So, but it's all, and the thing is, it sounds difficult, but it really is just circuit analysis. I mean, it's doing circuit analysis over and over and over and over and over again. You just get good at it. You get comfortable with it. It doesn't really frighten you. You could do nodal for sure. The difficulty with nodal is you don't know this voltage and you don't know that voltage, right? So it makes it more difficult to do nodal. And the other thing too is if I know the current through here, now I get all those losses really quickly. I don't know if my pen is dying or what. So if I had those, I can directly calculate losses. If not, now I got to calculate the voltage on each side of the resistor and then do V squared over R as the voltage drop. So there's just more work to do it. Usually calculating power losses is far easier with current than with voltage. But don't worry, we'll be using nodal analysis a lot moving forward. Especially next semester, because this semester, everything, we do some basic series circuits. Next semester, everything's in parallel. We do almost everything with nodal analysis next semester. We actually start out the semester building something with nodal analysis, believe it or not. And then we just spend the rest of the semester doing nodal analysis.
You opt for that.
Yeah, just to make Adrian happy, right? All right, so now we're going to go ahead and modify things a little bit. And this is a modification to simplify our analysis, because what we're trying to look at is how do we get power to move the system? In particular, how do we get power output relative to the change in the speed of operation? So we can come up with those torque versus speed characteristics. So the first thing we're going to do is we're going to be looking at an equivalent circuit. So we want to transform this stuff into a Thevenin equivalent. Okay. So you can see that I've transferred those two, but also I've transferred the input voltage to that. Why have I done that? Because now I have just one series circuit. So I've gone from V phase with all these resistors and inductors to just basically replacing this whole thing by the Thevenin equivalent. And if you remember the Thevenin equivalent, you can look at any 2 points, you open circuit, and then the voltage and the impedance that you calculate, which are in series with each other, is exactly the same regardless of how many components you have. So I'm replacing those three, the inductor, the two inductors and the resistor, and I'm also moving the voltage, that's the input voltage, and moving it on to that point. So now that I have this circuit, I have V Thevenin is equal to V phase, and I have just a voltage divider. Then I have R Thevenin is going to be equal, R Thevenin plus JX Thevenin is R1 plus JX at 1 plus in parallel with JXM. Anybody have any hard time? Are these two in series in parallel with those? That one? Are they in parallel with each other?
They will understand.
Tell me how you see it.
So you say that you leave out X2 and R2, right?
I'm looking just for the equivalent circuit. So what I'm looking for, let me put it on whiteboard. I'm looking for the equivalent circuit. Here. JXM, R1, JX1. So is R1 plus JX1 in parallel with JXM.
The cable looks like it.
Is there a short circuit on there? There better not be a short circuit, because if there's a short circuit, how much voltage am I going to apply to the motor? So they are or they aren't parallel?
But the cable is open. Which means it's just JXM.
So it's just JXM? Does anybody agree with Barzilai?
It's open at this side. It may just be this side.
Everybody agree? When you find the Thevenin equivalent impedance across 2 points,
It's just J.
not sure? What are the rules about finding Thevenin equivalents?
And off all other sources.
How do you turn off all other sources?
The voltage is the open circuit, the no,
Other way around?
yeah.
Tracing by the internal equivalent impedance in an ideal voltage source, how much internal impedance does it have? 0, right? It's a short circuit. Remember how we said this motor has to be energized. Isn't there a voltage source here? And how do you replace an ideal voltage source? With a short circuit. So I asked the question again. Are they in parallel with each other?
Yep.
They sure are. You can't forget about that external voltage source. It's an ideal voltage source, which means we have to replace it by its internal equivalent impedance, which is the short. So that's why we have this equation. Well, I should say this equation, they're in parallel. The voltage is still pretty easy to find, right? Because if this is not a short, if this is an actual power supply, and I'm trying to get the voltage over here, just voltage divider, isn't it? V applied or V, whatever the source voltage is, because it's a series circuit. Remember, it's equivalent, so I don't care what's happening over here. I'm just looking at the Thevenin equivalent. So I have JXM over the series combination of all 3 of those times my voltage. That's what I have here. And then if I want to get the magnitude, I just go ahead and calculate the magnitudes. We're going to assume that our magnetizing reactance is much bigger than X1, and it's also much bigger than R1. So we'll say V Thevenin is approximately equal to this. We'll also say that XM is greater than X1, and the combination of 2 is much greater than R1. So we'll say that R Thevenin will just approximate with R1 and times XM over X1 plus XM squared. And then X Thevenin is approximately X1. So now we can solve for I2 just by using our Thevenin equivalent. V Thevenin divided by Z total, right? Which is including the Thevenin equivalents. And you can see I've broken it up. So this really is a magnitude, right? Now my mechanical power is just 3I2 times R2 times 1 minus S over S. Just what we talked about for our equivalent circuit. And now our internal torque is just P converted divided by omega sub M, or P air gap divided by omega sub S. But more importantly, I can pull that from knowing what that power is. So to calculate my induced torque, I have an equation, 3 omega sub S, all times that. And then I can simplify it a little bit, and I have this equation. So now I have an equation of getting induced torque based on an equivalent circuit, a speed of operation, or the slip, and my, my applied voltage. And that's how I get this curve. That's how this curve is built. It's literally built using those equivalent circuits. So the induced torque is 0 at synchronous speed. Why is it at 0? Because there's no rotating magnetic field. There's no current induced. It's pretty linear between no load and full load. So that last little bit is pretty linear. So we're feeling pretty good about that. And there's a maximum torque that's called the pull-out torque, and it's about 2 to 3 times the rating of the full load. We also see that the starting torque is slightly higher than the full load torque, so it can actually start. The torque varies of the slip, but it also varies based on the square of the voltage. So one of the things that we do with induction motors, if we don't want to start them very hard, or they won't want them to draw a lot of current, is we start them at a reduced voltage. So you can actually buy, they're not as common as they used to be, but they're called reduced voltage starters that actually reduce the voltage to like 65% of nominal, which means they pull way less current. They pull a lot less torque out, but as long as it's enough torque to get the thing started, it should be able to get up and running. It's just going to take longer to start. And then if it runs faster, it converts from a motor to a generator. That's where we get rechargeable machines. Let's go back to our MATLAB script and let's continue. So I have this V Thevenin approach, this R Thevenin, this torque max, all this stuff. So let's continue on over here. So we're going to step. Oop, sorry, wrong one. Now I have all these parameters that I've got my maximum torque, which I can calculate. And where that max torque occurs is based on that slip. Okay. So I can put out about 228 Newton meters of torque when the slip is about 0.2. That's using a lot of approximations, right? Memorizing all equations. Why not I use MATLAB? And this is where MATLAB, you get to see the real power. Why not I do 1,000 calculations and vary slip and then just do a brute force curve plot? So I'm going to calculate that impedance matrix Z that we did before, and I'm going to allow it to vary as a function of slip. So I started at 0, then I go to 1 and 2 and 3 and whatever it is, not 0, 1, 0, 0.01, 0.02, all the way up until I get a slip of 1, or I have 1,000 slip points varying between not 0. Why not 0? Because if slip is 0, R2 divided by 0 would be infinity, so I can't calculate that. So I started at 0.01, a small number, and then I end at 1, and I put 1,000 points there. And then I just calculate Z. I solve for I pull out my rotor current. Then I calculate omega sub m because that's going to change based on the slip. And then my output power is I squared from the rotor circuit times that R2 times 1 minus S over S. And then I calculate the torque. So now I'm going to go ahead and plot that. So let's continue. Now I'm not going to do it 1,000 times, so I'm going to stop it. I'll be here all day. I'm going to move it, move my breakpoint after that. Set my breakpoint here and run it to this point. Now I'm going to go ahead and do my calculations, do a plot, and let's see. Whoa, looks just like it should. And this is just doing 1,000 calculations of I to R squared. So this actually generates the plot, the torque versus speed characteristic, just calculating the current using the equivalent circuit. Well, it looks pretty good. Let's compare our calculations for 228 and 0.9 and 198 essentially. In MATLAB, you can actually pull out in the matrix, you can pull out the max points. You can also, if you set up your points, you can actually see the X value is the actual speed, 1,441 RPM, and the torque is 230.8. Why isn't that 228, 227.8, and a slip of point or equivalent of 0.19, whatever? That's because the calculations we're doing in MATLAB are exact. Remember, I had to make some approximations about XM being much, much greater than X1 and R1. This is doing the brute force exact calculation. So in MATLAB, I actually use this indexing thing. So it digs into MATLAB and it looks at all the max values. So I'm going to run through. And let's see what MATLAB pulled out. So it pulled out maximum torque Let's see. It calculates out at 0.21 or 0.20, and then let's just go ahead and say T max 230.8. So this is where, you hate MATLAB, and I get it, but this is where the real power of it is, because just writing a little bit of code, a simple for loop to do this calculation 1,000 times, I could get a pretty precise plot, and I don't have to memorize all these equations. But if you want to do it on a calculator, that's when you got to do the V Thevenin and the Z Thevenin approaches. So pretty cool though, this all matches. And this plot, again, nothing up my sleeve. I did it all clear. You can see all the steps through, and it calculates all those. And you can verify that because if you look back in here, you can see that my T induced, I'll type in T induced, and it's got 1,000 elements. So it's calculating 1,000 different torques. And if you look at T induced for the very first one, it's putting out almost 0, right? We can't get to 0 because then when we calculate R2 over S at 0, it would be infinity. So we would get an error calculation. But at a slip of 0.01, which is 1%, we're getting 29. If you want it to be more accurate, you could start this out at, let's start it out at 0.001. And let's do it again. Now we're getting really close to 0, right? Because our slip is getting really small. Now we're 0.01%. So our output torque is 0.3. And on and on and on and on and on. You can go on this forever. Okay. Questions on how to do these calculations?
Why did you do the Thevenin? Do that again? What's the use?
Why did I do the Thevenin? Can I come over and borrow something from you? For a minute? Just gotta show TV land. This is why you would use the Thevenin, because you're using a calculator. If you can do this in MATLAB and code it, you don't need the Thevenin. How many people are going to use this? Everybody raise their hands. Yeah. But this gives you options. You can do it either way. You can do 1,000 calculations, and it doesn't take long, right? How long did MATLAB take to do this? Let's see. It's already plotting it. So less than a second to do the plot. Let me close it all completely and run it again. So tell me how long this takes to do the plot. Less than a second, maybe a second to display it. And you get the full curve. And you get more precision. The other thing too is I said find the max torque. But what if I said, hey folks, tell me what the starting torque is? Over here, you just click on this data point. And you tell me, oh, it has a torque of about 106. Or you can tell me here, what is it at 800 RPM? Well, it's around 160. I'm not obviously close, but you can just go ahead and look at the curves and you can obtain them this way. Anybody want this MATLAB script file, or I'll upload it to the course folder so you can access it there if you want. So I know when we had the tests, we gave it out, it was like, less MATLAB, but it's hard, right? Because you can see how, or hopefully you can see how just doing a little bit of digging in MATLAB gives you a lot of information. And the reason why we had to do the Thevenin equivalent is because we could just do one calculation, but with MATLAB, it's just, there's no point to it. You can just do it that way. Okay. Questions on anything? Good stuff. It doesn't sound like it. Good stuff.
On the slide.
Yes. Oh, let me go back. Let me share my screen. All right, let's bring up the slides. Which one?
On the Thevenin equivalent.
This one here, or?
Go out of it. Go on. Okay, you see the wind, the induced torque is called the power, the air gap over the WF, right?
Yeah,
That is what we use on the first example.
but it's really this, remember? It's P converted divided by omega sub n, but what we already said was P converted equals P air gap times 1 minus S. And omega sub m is equal to omega sub sync times 1 minus S. When we divide those two to get P converted, the 1 minus S is divided out.
Yes. But then now you can just use that formula, which is very easy, right?
Which formula?
The P converted over omega n or the P air gap over.
Whichever you want, yeah.
Yes, but then on the next slide, you get much more. Using, if we use the first one, we don't need to do the terminal. But then why did we do the terminal? Why did
Well, because this one is, I want to calculate the induced torque by any voltage and any slip. This is doing it for any value. Over here, right, I'd have to still calculate I. Correct? I can't get P converted unless I know what the current is using the equivalent circuit. So over here, that combines the current calculation all in one step. You still did all this work where you did this V Thevenin. You just did it right over here, right? You can see how I calculate I2. So with the I2 approach, you can either do what I showed you on how to do it with whiteboard and to get, right? You can do this value to get your I2, do the matrices, or if you recall from the PowerPoints, when we did the example, we did all this stuff, right? We did the Z total and the ZF. So you still have to do a lot of calculations. It's just that to get T induced, all I need is the voltages and the impedances, the values. I don't have to calculate current and do all that stuff. I can directly get torque from those values.
But then with the P induced, if, for example, if you do the test, are you going to give us the V terminal or we have to calculate the V terminal too?
That's up to you. You can calculate, you can write down the equation, you can do the calculations, you can do it either way. But be careful if you're in a test, and I said, what's the maximum torque on the machine? You either have to know how to calculate the Thevenin equivalence, or you have to do something else. And by the way, how do you calculate the Thevenin equivalent? We know how to calculate Thevenin equivalent. How do you know when you get max torque? I'll give you a hint for some of the material for next week. What's another way of saying max torque? You are transferring maximum power from the stator to the rotor. So you want max power transfer. That's when you're going to get max torque. So there's a way of calculating what that is by using the max power theorem. Remember that theorem that you were taught back in circuits? And you're like, why do I need to know this stuff? This is when you actually use it as an application. So you're taught it, but you actually don't do anything with it until starting to see that now. Any other questions?
So the only way to find the maximum of torque is just by using the terminal.
Nope. Can't you read it off the curve? You can use the equation if you're using your calculator, but if you've got a plot of the curve, I'll give you an option. I'll give you a piece of paper with a plot, or I'll give you all these parameters. Which one would you use to get the maximum torque? You look at the plot, right?
Yeah.
That's what we do in the real world. That's what we do in industry. We would go to the plot. But if we didn't have a plot, we could make one just by using this approach. And MATLAB, why do I use MATLAB? MATLAB works perfectly fine with complex numbers. You could do this in Excel, except Excel is very difficult to work with complex numbers, but it's just a bunch of equations. If you had the ability to do it, you could do, I don't know actually if MATLAB, I mean, if Excel, you can invert matrices. You probably could, but I just do all my calculations in MATLAB. And I've had to do plots in the past year or two that we've had to do magnitude and angle plots and all these different things. And you just do it in MATLAB and it's a piece of cake. I think it's a piece of cake. Okay, any more questions? Thoroughly bamboo. Oh, yes, sir.
So it's going back to voltage Thevenin, finding that, so it's slide.
V Thevenin and Z Thevenin.
Thevenin.
Yep, the Thevenin equivalent voltage and the Thevenin equivalent impedances. Once you have those, you can approximate what the maximum torque is. And you can approximate what the value of slip is when max torque occurs.
Okay, there's more about the actual equation. You have J, so J times exit one plus exit M.
Yeah.
One, and then the absolute value of voltage Thevenin, and J just disappears. Why is that?
Because it's an absolute value. The absolute value is magnitude only, right? There's no complex numbers, it's just the magnitude.
P squared, it's that way.
Right, so the J terms go away. Whenever you're talking magnitudes or angles, there's no complex numbers there. The angle itself might be complex. But, you know, to make it is complex, but the actual angle is just a number. It's the same thing as P and Q. Right? If we add P and Q together, then we have to have the J term. But when we talk about Q, I say it's 10 megabars. I don't say it's J 10 megabars, it's 10 megabars. But yeah, when we calculated Thevenin equivalence, we were looking at magnitudes essentially. That's what we see here. All right, any other questions? All right, well, if there's no other questions, have a great day. I'll see you all on Thursday. Take care, everyone.